Welcome to Tomversations, your monthly conversation with me, your host, Tom Hollingsworth, on a variety of technology topics. Today, I'd like to shine some light on an interesting subject, silicon photonics. And yes, that pun was absolutely intended. Let's dive right into this conversation. Now, we all know that data transmission happens electrically. We convert the ones and zeros of our data into electric pulses that are then sent down a wire. And what are those wires made out of? Well, in almost all cases, those wires are made out of copper. We use copper for network cables. We use copper for the traces on a silicon board. We use small pieces of copper inside of CPUs. No matter where we are, data flows electrically over copper. That's not always the case, though. For long distances, we use fiber optic cables. And for those of you who are not familiar, fiber optic cables use photons, which are a particle different than electrons, to send pulses down a transparent medium, usually some form of glass or plastic. This allows for much greater distances for data to travel, but it's not without its challenges. However, we're starting to see some very interesting things happening in the data transmission space. So anyone who has ever dealt with anything that is electric knows that one of the byproducts of large amounts of electricity coursing through a wire is heat. Um, some of you are old enough to remember incandescent light bulbs. I joke a little bit, but if you see this show in about 5 years, you'll know what I'm talking about. Incandescent light bulbs, which use a heated filament wire, produce light, but they generate heat. Compared to LED bulbs or even compact fluorescent bulbs, it's a massive amount of heat. Anyone who's ever built their own computer, purchased their own CPU, knows that it's a tiny little thing that requires a massive slug of copper sitting on top with some creative heat pipes to shunt the heat away as the CPU heats up during processing. Why? Well, when you have billions of transistors packed onto a small package, there is a massive amount of heat that gets generated. Companies have used very creative means in the past to shunt the heat away. But what if we could do it without the heat? Well, that's where silicon photonics comes into play. Just like fiber optics allows us to replace the traditional copper in a network cable with light pulses through a transparent medium, silicon photonics is investigating the possibility of replacing copper electrical wires with lasers and silicon. Now, before you get too far, you're probably thinking to yourself, wait a minute, Tom, silicon isn't transparent like glass. How is this going to work? Well, the funny thing is it turns out that silicon actually is transparent at certain wavelengths, specifically in the infrared spectrum. So according to IR, silicon is just as transparent as glass. That's a great idea in theory, right? Well, here's one of the problems. What wavelength do most lasers operate in right now? Yeah, that's right. They operate in the visible spectrum. They use photons after all, right? Well, in visible spectrum, the wavelength that our eyeballs see in, silicon is most definitely not transparent. So we have to create new lasers that are capable of doing that. The most popular kind are indium phosphide and gallium arsenide. I'm going to rely on my chemistry friends to give me a little bit of a background in what those do. But long and short, they're exotic lasers that allow us to pump data through silicon to provide communications. All right. Now, one of the biggest areas of research for this right now is in super high speed networking equipment. We had a great presentation from Andy Bechtolsheim of Arista several years ago where he talked about what the future of networking was going to look like. And one of the things that he said was above 400 gigabit optics, the size and heat produced by these optics was going to become something that was untenable for most networking equipment to be able to handle. Anyone who's ever picked up the optics necessary to light a 100 gigabit circuit, especially back in the day, would be shocked to learn that at one point they were the size of a standard iPhone and cost a small fortune. Today, through manufacturing processes and things like QSFP modules, we can get an optic for a 100 gigabit connection to be fairly small. But as we start ramping that up to 400 gig, 800 gig, and eventually 1 terabit Ethernet, the laser power required to pump that much data through that optic is going to be massive. And that doesn't even take into account the fact that the optics that you're handling have to be manufactured with absolute precision. When you're looking at something with an optical pulse, any kind of interference can degrade that pulse to the point of non-usability. Think about the Hubble Space Telescope. When it was launched, its mirror was ground just a couple of millimeters off, which effectively made the entire telescope useless because it couldn't see straight. What happens if a speck of dust gets in the middle of your laser path while it's trying to transmit data? You think you're going to get all the bits you're looking for? Most modern optics cost so much because they have to be produced in a hermetically sealed environment. And if you've ever spent hours polishing the end of a single mode fiber in order to make sure it's using as much bandwidth as possible, you know exactly what I'm talking about here. Silicon photonics eliminates this because you can manufacture the transmission medium just like you would any other chip, because it's silicon after all. And then all you do is put a laser on it and you pump the data through there. In fact, the small scale silicon photonics that would be replacing things like traces on a motherboard or possibly even chips, that's what gallium arsenide and indium phosphide lasers are really designed to do: produce their own laser light that allows you to send those signals. The ultimate goal for this is to create smaller, more efficient packages that produce almost no heat and allow us to create much faster transmission medium. So think about this. Modern laptops are built around a couple of design constraints, things like keyboards and screen sizes. But really, they're built around the idea that you can only pack so much processing power into a small form factor with very poor ventilation that has to sit on somebody's lap. And anyone who's ever used some of the older laptops that had massive fans and still did a bad job of pulling heat away can understand that laying a chocolate bar next to the exhaust fan produces a sticky little mess. But when you can add these types of communication media to these small devices with almost no heat being generated, the sky really is the limit. And one of the exciting places that this is taking on a new role is in one of my favorite topics, quantum computing. So if you'll remember back to a previous episode of Tomversations, we talked about the massive scale that quantum computers need to operate at in order to be able to give you the data that you're looking for. We talked about something called a qubit, which is the basic unit of quantum computing power. Well, one of the things that I didn't talk about in that video is that most qubits that we refer to today are actually not physical qubits. They're logical qubits. Well, what's the difference, you might ask? Well, a physical qubit is actually some piece of hardware that contains information. A logical qubit is a collection of physical qubits that include things like error correction. As you'll recall, I mentioned that thanks to Mr. Heisenberg, we know now that when we try to observe a qubit, we actually change the state of the data that's in it. So we have to use other qubits to infer what data is being stored in that qubit. So this means that for any one given logical qubit, it could be composed of hundreds or possibly even thousands of physical qubits in order to provide error correction. Well, think about that. If every bit you transmit is actually 100 or 1,000 bits, your bandwidth is going to get eaten up really fast, which means that even trying to create something like a 1,000 qubit quantum computer is going to be practically impossible. Because if your 1,000 qubit quantum computer requires 100,000 or even a million qubits worth of bandwidth, that's not something you can reliably create. Well, with silicon photonics, you can create systems that operate at that scale. Research that I've done indicates that most people believe that as silicon photonics starts coming online, you're going to see computers reach exascale computing capabilities. And that's just on, regular CPUs. Imagine putting all of those in the cloud. We really will reach a point where the capabilities of these devices are limitless. There's a lot of companies that are doing a lot of research into the technology. Intel is probably one of the most well known, along with Mellanox and some others. And it's very interesting to learn that even well respected journals like Nature have regular silicon photonics discussions going on. This is a technology that has the possibility to revolutionize not only networking as we know it by allowing us to get to terabit Ethernet, but also every part of computers. Essentially, if there is a copper wire somewhere, silicon photonics has the potential to replace that with a higher speed, smaller package, and less heat option. I hope this look at silicon photonics was interesting to you. It's an evolving technology that will be interesting to follow along with for the next few years. Who knows? Maybe one day I'll be recording an episode of Tomversations on a computer that uses silicon photonics exclusively. Well, let's just have to see. You should definitely head over to our website, gestaltit.com, to check out more great content like this, including our Checksum series, our on-premise IT roundtable, and a variety of other great videos and articles. I'll be back next month with another great topic, and we hope that you'll be able to join in and follow along with us. Thanks for watching.